Current Alzheimer's treatments offer a stark, limited choice. Physicians can prescribe cholinesterase inhibitors that provide a modest, temporary delay in symptoms, or they can turn to newly approved anti-amyloid antibodies, which carry extremely narrow treatment windows and severe risks of brain bleeding and edema. These options highlight a regulatory bottleneck, where truly disease-modifying therapies remain absent. In 2023, research out of McGill University introduced a highly unusual dataset. Investigators Andrew Calder and Siddhartha Bhattacharya administered a single dose of psilocybin to 3 TXG-AD mice, a specific transgenic model engineered to express 3 distinct human Alzheimer's mutations. This chart shows the tau phosphorylation levels measured 4 weeks after that single dose. At both the AT8 and AT180 epitopes, the primary markers of the destructive protein tangles in Alzheimer's, the psilocybin-treated group shows an approximate 35% drop compared to the control group. In this clinical context, psilocybin functions as a rapid-acting psychoplastogen. It executes a structural counterattack across 4 distinct biological dimensions of Alzheimer's progression. Alzheimer's pathology is not a localized failure. The disease dismantles the brain simultaneously across multiple scales, operating from the intracellular molecular level up through localized neuroinflammation, all the way to macro-network dysfunction. To understand how one molecule impacts the system, we have to track psilocybin's pharmacological cascade from the top down. We will follow the signal from the brain's macroscopic architecture, pushing through cortical tissue, ending precisely at the synaptic membrane of a single pyramidal neuron. The biological tension centers on how a single agonist, binding primarily to the serotonin 2A receptor, is uniquely positioned to interact with all 3 dimensions of this neurodegenerative collapse. Analyzing this mechanism requires moving beyond the classification of psychedelics as psychological aids. The focus remains on the physical, receptor-level cascades triggered inside the neural tissue. The first scale of failure is structural. In the Alzheimer's brain, concentrations of brain-derived neurotropic factor, or BDNF, drop by 30 to 40% in the hippocampus. Without this critical protein, neurons lose their structural support, which leads directly to rapid synaptic pruning and cell death. This diagram illustrates psilocybin's bypass mechanism. Normally, BDNF activates the TRKB receptor to maintain cell health. Psilocybin acts as a psychoplastogen that bypasses the missing endogenous BDNF entirely. It directly triggers the exact same TKB downstream signaling cascade without requiring the original protein to be present. By initiating this signaling cascade, psilocybin can rapidly force the growth of new dendritic spines on the pyramidal neurons. These are the physical sites of synaptic connection. The timeline of this structural growth is measurable in hours and days. This stands in sharp contrast to the decades-long timeline of neuronal degeneration that characterizes early-stage Alzheimer's. This pharmacological bypass artificially forces a surge of neuroplasticity. It triggers structural regrowth exactly where the Alzheimer's brain has lost its natural regenerative capacity. This cortical map highlights a structural paradox. The serotonin 2A, or 5-HT2A receptors that psilocybin targets, are the exact same receptors destroyed by the disease, showing up to a 40% reduction in density in the Alzheimer's cortex. With nearly half the targets gone, every surviving 5-HT2A receptor becomes a highly leveraged node for pharmacological intervention. These surviving receptors connect directly to the brain's immune axis. When psilocybin agonizes the 5-HT2A receptor, it initiates a signal that suppresses NF-κB. That is the master transcription factor driving inflammatory behavior in the brain's immune cells, the microglia. By inhibiting NF-κB, this receptor activation physically halts the production of specific pro-inflammatory cytokines, including interleukin-1 beta, tumor necrosis factor alpha, and the cytokine interleukin-6. Interrupting this localized inflammatory cascade removes the highly toxic microenvironment that amyloid plaques require to rapidly propagate and damage surrounding tissue. Moving past the cell membrane and inside the neuron, we encounter the structural microtubules. In Alzheimer's disease, hyperphosphorylated tau proteins begin detaching from the microtubules, causing the neuron's internal scaffolding to collapse. We can trace the pathway initiated earlier at the membrane.
When psilocybin activates the TKB receptor, it sends a continuous signal downward through the AKT and PI3K intracellular signaling cascades. This specific cascade directly terminates at a key enzyme. The AKT and PI3K signaling places a hard block on the activity of glycogen synthase kinase 3 beta, or GSK3 beta. GSK3 beta is the primary driver of tau hyperphosphorylation. By inhibiting its activity, the cell physically prevents normal tau proteins from misfolding and aggregating into lethal neurofibrillary tangles. This targeted enzyme inhibition is the specific molecular mechanism that explains the 35% drop in tau phosphorylation observed in the McGill transgenic mouse models. Zooming out from intracellular enzymes to whole brain networks, the pathology scales up to affect the default mode network. This is the system responsible for mind-wandering and self-referential thought. In early Alzheimer's, the default mode network exhibits a severe regulatory failure. It cannot suppress itself when the brain attempts a focused task, locking the network into a continuous state of metabolic hyperactivation. This localized hyperactivation correlates with, and likely drives, the earliest and most dense accumulation of amyloid plaques in the network's central hub, the posterior cingulate cortex. These side-by-side fMRI scans illustrate psilocybin's most robust acute signature. The image on the left shows an overactive default mode network. On the right, acute psilocybin exposure forcefully suppresses this activity, profoundly desynchronizing the network. This acute desynchronization forces the hyperactive network to stand down. It provides a macroscopic functional reset, offering a systemic recalibration that operates in tandem with the localized molecular repairs. Preclinical data provides a map, but the history of neurodegenerative research shows a high failure rate. Many compounds have successfully treated transgenic mice, only to fail completely in human phase 3 clinical trials. To bridge this translational gap, researchers are now moving into human safety trials. At Johns Hopkins University, early-stage pilot studies led by Dr. Albert Garcia-Romu are bringing these mechanistic theories into the clinic. These initial trials employ a dual measurement design. While they track psychological endpoints like depressed mood, they simultaneously run rigorous cognitive memory batteries to search for structural and functional biomarkers of disease modification. Translating this protocol to an Alzheimer's population introduces unique logistical and ethical friction. Classic psychedelic therapy demands extensive psychological preparation and integration, which requires a level of cognitive consent capacity that moderate to severe patients no longer possess. Because the requirements for psychotherapeutic preparation and informed consent are so strict, researchers must target a very narrow, early window for clinical intervention. This timeline visualizes that actionable prodromal window known as mild cognitive impairment, or MCI. In this stage, the disease is identifiable, but the target neural networks remain largely structurally intact. Patients in the MCI stage retain the decisional capacity required for ethical consent. They are currently the only clinically viable population capable of safely navigating the intensive demands of a high-dose protocol. The therapeutic objective centers on circuit-level resilience. Rather than attempting to reverse established neurofibrillary tangles, the protocol aims to strengthen the surviving neural architecture to maintain functional capacity. The biological argument points to a singular intervention. It bypasses the collapse of BDNF, halts microglial inflammation at the 5-HT2A receptor, inhibits the tau-destroying GSK3 beta enzyme, and forcefully resets macroscopic networks. The molecular cascade is documented. The ultimate horizon rests on clinical execution, translating this acute, multi-scale plasticity into persistent cognitive preservation for human patients.